Hello and welcome to the wonderful world of quantum mechanics. I just want to begin by saying that I like gardening. So let me draw a plant pot. And we're going to see the supreme relevance of this plant pot to quantum mechanics in a couple of minutes. I just want to begin by saying what we're going to do today is to go through chapter 1 of the lecture notes, and those lecture notes are available here and also online. Those lecture notes have got exercises which are an intrinsic part of the course, and those exercises are spread throughout the notes, and the full solutions. So all those exercises are available online. But because I'm a bit of a greenie, I won't be giving printouts of those solutions. But both lecture notes and solutions are available online. My name's David, and I'm here to talk quantum mechanics with you. So let's go back to the plant pot. Now suppose that I plant a lemon seed, and that lemon seed grows into a lemon tree. Yep. So this is our lemon tree, and that this lemon tree grows 1 metre in 1 year. So we're scientists, we make observations, we observe that our lemon tree grows 1 metre in 1 year. Suppose I was then to say, I'm a logical person, the lemon tree grew 1 metre in 1 year, therefore it will grow 1 billion metres in 1 billion years. 1 metre in 1 year, extrapolate, 1 billion metres in 1 billion years, or 1 trillion metres in 1 trillion years, or 1 trillionth of a metre in 1 trillionth of a year. Now, all of those statements are unwarranted extrapolations of an initial observation, and that's the key point. One can take observations, but one can't extrapolate them too far. Now, moving from lemon trees to physics, the history of physics is littered with unwarranted extrapolations, and I want to give you 4 examples, which will lead us beautifully into the subject of quantum mechanics. So the first example of an unwarranted extrapolation in physics is the idea of the flat Earth. Now, I don't know about you, but I look at the floor here and I see that it's flat. And nothing you say is going to convince me otherwise. The floor is flat. When I play billiards, when I kick soccer balls around on the floor, I'm working with the excellent assumption that the floor is flat. So there's an initial observation, akin to the 1 metre in 1 year, except now we have a physics observation that in my immediate vicinity, and note the qualification, in my immediate vicinity the world looks flat. Unwarranted extrapolation, the world is flat over any distance. There's one example of an unwarranted or incorrect extrapolation in physics. As a second example, the idea that matter is a continuum. If I look, for example, at a glass of water, or a stick, or a lump of linoleum, or at the inside of my hand, it looks continuous. Again, I don't see any atoms. I see a continuous matter in my hand. I see continuous matter in a liquid in a glass of water. That's an observation. Unwarranted extrapolation, matter is continuous down to arbitrarily small length scales. We know that atoms exist. Matter is not continuous. If you look at a small enough scale, for example, 10 to the power of 10 times smaller than a metre, then we start to see individual atoms. So the idea that our eyes tell us that matter is a continuum is an observation that can't be extrapolated down too many orders of magnitude because it breaks down. A third example, here's a wrong equation for you. F equals ma, force equals mass times acceleration. Now this is an embodiment of everyday common sense, the cornerstone of classical mechanics. It's also bullshit, right? Let me prove it to you. I take an object of some mass, I apply a constant force F equals ma tells me that the acceleration, the force is a constant, the mass is a constant, hence this accelerates at a constant rate. Let it accelerate at 1 metre per second. If you wait long enough, if you wait arbitrarily long, it'll have an infinite speed. F equals ma, uniform acceleration, push for as long as you want, push for arbitrarily long time, and the thing will go arbitrarily fast. You want infinite speed? No problem. F equals ma says that you can have an infinite speed. Here we see a theory breaking down. Observation regarding gardening breaks down if you push it too far. Flat Earth hypothesis breaks down if you push it too far. The idea of matter being a continuum breaks down if you push it too far. This central law of classical mechanics breaks down if you push it too far. We know from experiment, empirically, that nothing can travel faster than the speed of light. Now, maybe they'll do an experiment tomorrow which proves that wrong, but for now, no experiment has seen particles travelling faster than the speed of light. Therefore, this equation is wrong. Now let me nuance that statement a little bit. This equation is not wrong matter, this statement's not wrong either, and neither is this. The Earth is flat. Don't quote me on that, but the Earth is flat if you don't look too far over length scales that are too big. Matter is a continuum, provided you don't look at too small a length scale, and F equals ma works, provided you don't push for too long. In other words, theories of physics, in this context, have domains of validity. This equation is not wrong, it just has a limited domain of validity. F equals ma works fine if you don't push for too long, if you don't accelerate too fast and so on. Theories have domains of validity, but ultimately this, if you try to push this equation, bad joke, if you try to push this equation beyond its domain of validity, then it will break down. But this is an example of classical mechanics breaking down. And that leads me to my fourth example. Excellent. This leads me to my fourth example, which is classical mechanics. In many respects, classical mechanics, of which F equals ma is one part, is an embodiment of everyday common sense laws, everyday intuition based on masses that we can directly apprehend, like bits of chalk or whales or cars or ball bearings. Everyday common sense based on the time scales that we can directly apprehend, and everyday common sense based on lengths that we can directly apprehend. So let's look into this a little further. Why should classical mechanics work? If you're looking at something that's 1 billion times smaller than the smallest thing you can see, that would be as absurd an extrapolation, an unwarranted extrapolation, as a statement that my lemon tree will go 1 billion metres in 1 billion years because it grew a metre in a year. This is the embodiment of everyday laws of common sense, and we can't directly apprehend timescales, masses or lengths which are smaller than a certain amount. So what's the smallest timescale that we could directly apprehend? Just roughly, order of magnitude. A second, a tenth of a second, hundredth of a second? Millisecond, beautiful. So just very roughly, the smallest time that we could directly apprehend with our senses is a millisecond. How about the smallest mass? Speck of dust in your eye. What's the smallest mass that you could directly apprehend? Milligram, sounds good. By the way, you don't have to agree with what's in the notes. In fact, I like it when people disagree with me. What's the smallest length that we could directly apprehend? Tenth of a millimetre. Does someone want to go smaller than that? No, cool. Tenth of a millimetre, it is. 10 to the minus what? 4, thank you. Now think lemon trees, right? What's the shortest time scale in theoretical physics? It's 10 to the minus 23 of a second. This is a characteristic time over which, for example, the strong interaction takes place. It's the time it takes light to travel the width of one proton. There are objects in physics or processes in physics which take 10 to the minus 23 of a second. That's 20 orders of magnitude smaller than the smallest time that we can directly apprehend. It's 100 million times smaller in time. The lemon tree is not going to grow 100 million metres in 100 million years. Why the hell should classical mechanics, which is based on common sense, everyday common sense, which can directly apprehend times no shorter than 10 to the minus 23 of a second, why should it extrapolate down 20 orders of magnitude? If it did, that would be weird. The point here is that quantum mechanics should be weird. Yes, classical mechanics has a domain of validity. Yes, classical mechanics breaks down. If it didn't break down, that would be truly bizarre. People often tell you quantum mechanics is weird, and it is, but it should be. Quantum mechanics should be weird. Why the hell should your everyday common sense extrapolate down 20 orders of magnitude in time? Let's go to masses. We said that the smallest mass we can directly apprehend is, so it was 1/10 of a milligram, wasn't it? Well, what's the mass of a proton? Roughly 10 to the minus 30 of a kilogram. That's 26 orders of magnitude smaller, right? 100 million times smaller than the smallest mass we can directly apprehend. Why should the laws of classical mechanics extrapolate down 26 orders of magnitude? If classical mechanics worked for electrons, that would be truly bizarre. Classical mechanics doesn't work for electrons, and that's part of the point. This is why we need quantum mechanics. The smallest length that we can directly apprehend, 10 to the minus 4, but the width of an atom is 10 to the minus 10 of a metre. and the width of a proton or a quark is orders of magnitude smaller still, 1,000,000 times difference. Again, the laws of classical mechanics have no right to work. We've certainly got no a priori right to assert without testing, without asking nature, without doing experiments, whether the laws of classical mechanics work for this microscopic world of tiny times, tiny masses and tiny lengths, tiny relative to the smallest mass, length and times that we can directly apprehend. So that's a nice segue into quantum mechanics. I've explained why quantum mechanics should be weird, and this idea that our theories have domains of validity, and we should expect a priori, an experiment does indeed tell us that at the atomic level and smaller, classical mechanics breaks down. So let's now move into some watershed moments, some key moments in the history of quantum mechanics. So I'll just abbreviate this as watersheds. In other words, important moments in the development of quantum mechanics. Physicists at the end of the 19th century were very, very arrogant. They basically said, apart from a few small tweaks, we know everything, right? How wrong they were, because the quantum revolution came in, special theory of relativity came in, general relativity came in, and screwed up everyone's heads. But made the point that everyday common sense doesn't extrapolate. Again, theories have domains of validity. Now, every now and then, I encourage you to go outside and look at the stars, and look at them with a certain childlike sense of wonder. What do I mean by that? There you go. What the physicist does is to study with as precise and analytical a mind as possible the physical world. But the physicist, in my opinion, should also have very much a childlike sense of wonder at the beauty of the world. Now, looking at the stars is something a kid can do. Looking at the stars is something you can do, but you can see with much more profundity. But the simplicity of the child, I think, is also important. Why the hell am I talking about this now? Because I believe it, and secondly, because what I want to do now is to revisit some things that you've learned several years hence. This lecture is going to be fairly simple. It'll get more advanced later, as you can see from the lecture notes, but I want to make the point that I want us to examine some very elementary things, things that you've seen before, but I want you to look at them with deeper eyes. And the first, and this is going to be, I'm losing it for a bit. I'm going to look at three things in particular. This is not a complete history of quantum mechanics. Rather, this is just looking at three particular key moments in quantum mechanics with the benefit of the hindsight that you have now that you're studying at level 3. So the first thing we want to look at again is the photoelectric effect. Again, I know you've met this before. Again, I know it's revision, but I want us to revisit this. So photoelectric effect. Building on from some experiments of Hertz in the late 19th century, we have Leonard investigating the photoelectric effect. So what is this? We have some battery which forms a part of an electric circuit with some resistance R and potential difference V. And this is going to be considered attached to two polished metal plates which respectively form a cathode and an anode. We put these polished metal plates inside some evacuated glass container. There it is. And this evacuated glass container, or evacuated glass tube T, we're now going to illuminate this thing with ultraviolet light from some source S. And what we observe is that if the light is off, then no current flows through this circuit. If, however, the source is on, then current flows through this circuit. Current, little I, flows through this circuit. And what do we observe? Again, you've seen this before. The current is proportional to the intensity. I'll denote intensity by capital I. It was observed that current was proportional to intensity. It was observed that the speed v of the ejected electrons is not a function of the incident intensity. It was observed also that the speed v of the ejected electrons is a function of nu, which is the frequency of illuminating light. Lastly, it was observed that as soon as the light is switched on, electrons begin to flow immediately. Again, this is a revision, and again, you know that this can't be explained using the classical laws of electromagnetism to describe the electromagnetic field emitted by the source. And people tried, right? People tried and they failed. Then Einstein came along and said something which in retrospect is a bit conservative. Some ancient Greeks postulated that matter is not a continuum, but that atoms exist. Atom, by the way, in ancient Greek is from the Greek word atomos, which means that which cannot be divided. The Greeks knew that matter could be chopped up into little bits, that matter was discrete. Einstein, okay, it was radical, but it was also in some sense conservative, said that light, such as the light filling this room, is also chopped up into little bits. Now, instead of speaking of discrete little bits, let's use the word quantum. Singular is quantum, plural is quanta. So when we speak of light as being made of quanta, namely photons, we speak of chopping up the electromagnetic field into little discrete packets, little discrete pieces of light, which are called photons. Einstein, by the way, did not come up with the name photon, but he did postulate that the electromagnetic field be considered as little atoms of light. So matter is not a continuum, known for a long time. The Greeks postulated it thousands of years ago, but it began to become mainstream in the early 20th century, that late, believe it or not. Einstein was just saying, same thing happens for light. Light is chopped up into little bits called photons. And this photon hypothesis, remember when Einstein wrote this, people thought, nah, this guy's off his tree. And anyway, he's just a patent clerk, what the hell would he know, right? So this very, very radical idea. And people said, nah, this is bullshit. I'm going to try and explain this with the laws of classical electrodynamics. And it wouldn't work. None of these things could be explained properly with classical electrodynamics. But if you think of light as a photon, if you quantize the electromagnetic field, you consider atoms of light, then this follows through directly. And I've got a quote from Einstein here. The energy of a light ray spreading out from a point source is not continuously distributed over increasing space. It's not a continuum, but consists of a finite number of energy quanta, which are localized in points of space, which can move without dividing, and which can only be produced and absorbed as complete units. So just to quantify this with some mathematics, the energy of each photon is proportional to its frequency nu, constant proportionality being Planck's constant h. If we ask what is the kinetic energy of the ejected electrons, which are called photoelectrons, I know that I was bagging Newton's laws before, but let this photoelectron be moving with sufficiently slow speed v that half mev squared works. This is the kinetic energy. M subscript E is the mass of the electron. This is the kinetic energy of the ejected electrons. That's just going to be the energy of the incident photon minus the so-called work function, which is the energy required to dislodge an electron from the metal. So this is the first key moment in the history of quantum physics where light is treated as a quantized electromagnetic field. Fair enough. And again, I want to emphasize, people did not like this at all. The first experiments which were done on this, which won the people the Nobel Prize, they initially set out to disprove these absurd ideas of Einstein. Yep. The history of physics often proceeds like that. Next one, Compton Effect. Similar story. You've got Arthur Holly Compton in his laboratory, and he's taking lumps of matter and illuminating them with X-rays and asking the question, what happens when I illuminate a lump of matter with an X-ray? Now matter is filled with atoms. The X-rays actually scatter from the electrons. So let's consider an electron in an atom. Compton just wanted to understand his experimental results. Compton wanted to understand what happened when X-rays illuminated matter. And he tried classical electrodynamics. And for years he did the calculations, and for years they didn't work. Then he read this crazy paper by Einstein and thought, let's treat the X-ray as a photon, as a billiard ball with a discrete amount of energy E, or with a discrete wavelength lambda, or with a particular frequency nu. So you have an X-ray coming in. Often we use the symbol gamma for an X-ray, lowercase gamma. This strikes the electron, which we're going to approximate as approximately stationary, this electron in an atom. After the interaction, the electron speeds up, so it's going to recoil with some speed v. It's going to recoil, it's going to be deflected through some angle, which I don't care about. I could if I wanted to, I'll call it phi, I'm not going to calculate it. The photon is scattered through some angle theta. And it was a scattered photon that Arthur Holly Compton detected. Now the electron is gaining energy, therefore the photon must lose energy. The wavelength of the photon, let's call it lambda prime. Lambda is the wavelength of the photon before. Scattering in lambda prime is the wavelength of the photon after. This process is called Compton scattering. It treats light as a billiard ball. It quantizes the electromagnetic field. It treats light as a quantum, namely a discrete piece. So Compton did this calculation. It takes about half an hour, and you'll be doing it in exercise 2. Again, I want to emphasise exercises are spread throughout the notes. All the solutions to the exercises are available online. I'm handing out hard copies of the notes, but the solutions are just online. I do that because I'm a greenie and I want to save some trees. Secondly, you should only glimpse, in my opinion, at the solutions when you're stuck. As soon as you get the hint you need, you put them away. All right, here we have Compton scattering. Now, the formula which explained this is called the Compton formula. It's equation 3 in the notes. This is the difference between the wavelength of the photon after and before scattering. We'd expect it to be positive because the wavelength gets longer. There's some constants, positive constants of proportionality. Mass of the electron, speed of light, h is Planck's constant. We have the sine squared of half the angle. Again, this is a Nobel Prize winning calculation, which you do in exercise 2. This thing is manifestly positive, as it must be. Fair enough. This is the Compton formula. I want to make a point that I'll come to many times during this course. This is not just a formula which has a bunch of Greek symbols in it. If you stare at this long enough, common sense should leap out at you. In other words, there's many, many physical trends here. You look at this and you graph it, and you ask the question, what happens if I set h bar to naught? What happens if h bar were to double? What happens if the mass of the electron were to be bigger or smaller? What would happen if the speed of light was bigger or smaller? What happens if theta is very small? What happens if theta is 0? What happens if ... Ask all those what happens if, and the formula will behave in a particular way. If you were to double the mass of the object being scattered, this wavelength difference would halve. What does that mean physically? If you were to make the angle 0 or 90 degrees, how does this behave? That's a mathematical question, it's a trivial one, but then I ask you to interpret it physically. The point is you can stare at formulas, and if you stare at them long enough, something magic happens. You actually see how that couldn't be otherwise. If you understand deeply enough, the formulas should become trivial, not because you're a genius. I'm not a genius. I have to work hard at this stuff and sweat for days, weeks, hours to understand stuff. But if you truly understand any formula, you should be able to stare at it deeply until you tell yourself it could not be otherwise. Could you write it down on inspection? Do you understand why it behaves the way it does when you double quantities, turn them off, and so on? Now, I'm not going to do that for you here, but I will do that many times during the course. As a challenge to you, I want you to get total understanding of this formula. You derive it in the exercise, but then I want you to stare at it for 10 minutes or an hour and discuss it with your friends, of course, until it makes absolute sense in the sense that I've described. The third example of a watershed moment in quantum physics. Excellent. It normally takes me a few lectures just to get that amount of momentum just right so it just touches the top. Too much and it bangs off the top, which is bad. Too little and it needs to be pushed up a bit. All right, third of three key moments in quantum physics is atomic spectra. And again, I want you to look with the eyes of a child again. From one perspective, this is boring revision. But in my opinion, this idea of atomic spectra is the way that you can see quantum mechanics directly with your eyes. I'll explore that point soon. So we have some metal container which has some window in it, and this is filled with some hot elemental gas, for example, glowing sodium gas. And because it's glowing, there's light emitted. And we pass this light through some prism, the light is refracted, and we have some film which I've called G in the notes. Now what you don't see is a rainbow-like continuum here. What you see is discrete lines of different colours, which are called spectral lines. Again, look at this like a kid looking at the stars. This is quantization staring you in the face, right? Because what's happening is you have the atoms, if the atom could have energy, any energy level, this is an energy diagram, low energy, high energy. When the atom goes from some high energy to some low energy, that energy is converted into a photon, which comes through the system. If any energy were allowed, between 0 and some maximum, if any energy were allowed, then any energy difference would be allowed, and hence any colour would be allowed. But you don't see the rainbow light continuum, you see discrete lines. This is telling you directly that only certain discrete energies, E0, E1, E2, E3, etc., are allowed. And when we see a photon, the atom is de-exciting from the mth energy state to the nth energy state, and in doing so it radiates a photon. What is the energy of that photon? What is the energy of that photon? Well, it's precisely the difference between the two energy states, and the fact that the energy of the photon, which becomes its colour, is quantized, means that these things are quantized. So when you see spectral lines, you're seeing the quantization of energy levels in the atom directly. Again, learn to look at this like a child. The energy of the photon is related to its wavelength lambda as follows. And you get to prove this stuff in an exercise. So when we stare at this atomic spectra, as I said, you see quantization in action. Now, Bohr had a model for the energy levels of the hydrogen atom. If we have n being an integer, 1, 2, 3, 4, etc., what did Bohr say the energy levels of the hydrogen atom were? What is the nth allowed energy level of the hydrogen atom? This is exercise 3. When you do that, you win another Nobel Prize. This makes a point, by the way. I say that you can knock off Nobel Prize winning calculations in 10 minutes. The genius is when you can do the thing for the first time. Genius is not when you fill out 60 pages of complicated mathematics. Genius is when you stare at something for long enough and see the simplicity. I've heard, for example, special relativity described accurately but unfairly as a trivial application of linear algebra. From one perspective, special relativity, which I'll teach in PHS3131 for those doing it, is a trivial application of linear algebra. But being the first to see that and understanding its physical implications is a different thing altogether. So the key point here is genius consists in seeing simple solutions to difficult problems. And whether you're a management consulting working in industry or someone trying to improve quantum mechanics, it's still the same story. The idea of being able to see simple solutions to difficult problems is, in my opinion, the most valuable skill that one could have as a researcher, whether in a fundamental or an applied setting. So simplicity comes at the cost of great work, and also the quest to, again, see the simplicity. Secondly, I'm much more impressed by a simple, elegant solution to a problem than by bulldozing it. If you bulldoze it if you have to, and some problems have to be bulldozed, in other words, need 60 pages of advanced mathematics. But if you can write down the answer on inspection, or do it in half a page, then that's much more impressive because the physics of it is transparent and the mathematics is much more elegant. All right, so what did Bohr say? Well, Bohr came up with some formula, some constant, which I've called squiggle. It's in equation 6, and n squared. So this is Bohr's formula. The energy of an electron is negative. This reflects the fact that the electron is stuck or bound in an atom, and I invite you to think about that a little more. The energy of the electron is negative. There's a bunch of constants here given explicitly in equation 6, and we have a 1 on n squared law. The Bohr derived this using what's called a semi-classical argument. Semi-classical means the following: half quantum mechanical and half classical. Semi-classical arguments are ultimately contradictory. You try and push Bohr's theory of the hydrogen atom any further than the hydrogen atom and you don't get very far. You'll never hear Bohr's theory of the helium atom because it doesn't work, but it has a restricted domain of validity to one atom. But apart from that, it's still very good. It mixes classical concepts, namely a billiard ball orbiting a nucleus, and quantum concepts, quantization of angular momentum having certain quantized values. Nevertheless, he got this formula using an argument based on semi-classical means. Now imagine that you're Bohr and you've just derived the Bohr formula and you're thinking, I need to publish this, but are my colleagues or my mates going to tell me I'm crazy? So what you need to do is you need to take all the available data and see if it explains that available data. Now if we cast the clock back, this is early 20th century stuff. If we cast our minds back to late 19th century, to 1885 in particular, there was a school teacher who looked at the spectral lines of hydrogen, and this school teacher, called Balmer, noticed the following, that the wavelength of the spectral lines known at the time, let's index them with an integer p, p is 1, 2, 3, 4, etc. The wavelength of those known spectral lines was some constant, known as the Balmer constant, times this formula here. And Balmer came up with that formula purely empirically. He just guessed the formula and it worked. If you're Bohr and you've just got this formula here, which is supposedly more general, then you should be able to derive the previously known empirical result as a logical consequence of your result. In other words, you should be able to go from equation 6 to equation 8 in the notes. By the way, note that the reduced Planck's constant, h bar, which I'll often just call the Planck's constant, is Planck's constant on 2 pi. Just for economy of words, I'll often speak of both h and h bar as Planck's constant. I mentioned before that I like it when people disagree with me or question things. Are there any statements that I've made so far that you'd like to question and or discuss and or nuance in more detail and or disagree, because I like that very much? Who'd like to kick off? Was Newton wrong? F equals ma breaks down. Was Newton wrong? So, sorry? Yeah. Newton was wrong, yes. So can you elaborate on why Newton was wrong?
He made a formula that applied to things that were sort of observable at the time.
So he made a formula that applied to things that were observable at the time?
And he didn't take into account sort of like the long view of things or like the scale of nature.
So he didn't take into account things such as the scale of nature, phenomena that were beyond observations at the time. But suppose I was to come back and say, if you're building a bridge or playing billiards or working out the trajectory of a satellite, then unless it's a high precision satellite, Newton's laws work fine. Therefore Newton was right. I'm asking the wrong question. What would be a better question than is Newton right or wrong? Sorry? Is it accurate? Beautiful. Is it accurate? Newton's equations work with acceptable accuracy if you're mucking around with billiard balls or low precision satellites or building bridges. But if you want a very, very high degree of accuracy, for example, suppose that you're designing a global positioning system, Newton's laws equations don't work with global positioning system satellites, because the precision that you need in global positioning system, you want to locate someone on the Earth to within, let's say, a few metres, or if you're in the military, much smaller scale, then Newton's equations don't cut it. The satellites are not moving at appreciable fractions of the speed of light, but the satellites in GPS need to be sufficiently accurate to build on your point that Newton's equations don't cut it. You need both special relativity and general relativity, not quantum mechanics, but special and general relativity, in order to explain the motion of satellites. So if you want very, very high accuracy, then you may need to move beyond a particular theory. But having said that, if you're playing billiards, there's no point doing quantum mechanics. Doing quantum mechanics to work out the trajectory of a billiard ball is as pointless as using a jumbo jet to fly down to the milk bar, right? Theories have domains of validity, but use the simplest theory that does your calculations to the accuracy that you require. If I'm throwing a tennis ball, yes, I could do relativistic quantum mechanics to work out what happens when I hit the tennis ball, but there's no point. Just do F equals ma and put in some wind resistance and you'll be fine. So theories have domains of validity. Ask yourself what accuracy do I want to work with, and then choose the simplest tool that will get the problem done. Another point here, again building on this question of was Newton wrong? If I say F equals ma and I have all the concepts of classical mechanics and they work fine to a particular accuracy with a particular class of problems, but then I bring in quantum concepts, which is the subject of this course, which looks at the world quite differently. Is a billiard ball a quantum object or is it a classical object? Well, it depends on the accuracy to which you want to work, but the concepts themselves are contradictory. So the point is, a billiard ball is not a classical object. A billiard ball is not an object as described by Schrödinger theory, as we'll develop in this course, because there's 5 or 6 different theories you could use to describe billiard balls, each of which have different domains of validity and different degrees of complexity. Again, one chooses the tool for the job, but the physicist doesn't have an absolute view of the world. The physicist builds models. I could model a light electromagnetic field many different ways. I could model it as a ray. That works fine if I'm doing ray tracing to build glasses. I could model the light as a photon, a billiard ball photon, as in the Compton effect. I could model light as a polarized electromagnetic field. I could model light as a complex scalar field. I could model it as a quantized electromagnetic field. According to an easy version of quantum electrodynamics, I could model it using the most sophisticated version. 6 different ways to describe the same thing. Again, I'll choose the tool to do the job. Is light 1, 2, 3, 4, 5 or 6? Well, it's none of them. It depends which way I'm looking at it, and a different set of concepts for each. One further thing. Stimulated by the question was Einstein right? So I keep saying Einstein. I teach relativity, but not until week 5. Let's take classical mechanics and let this X describe a phenomenon that can be described with classical mechanics, a billiard ball on a table. Let me draw a bigger bubble and let's have some phenomenon Y. And phenomenon Y can't be described classically, but it can be described quantum mechanically. Yep, so this is an example of a phenomenon, such as electrons in an atom, which can't be satisfactorily described using classical mechanics. Quantum mechanics has a domain of validity which is wider than classical, but there will be phenomena, such as Z, which quantum mechanics can't explain. But this begs a logical question. Classical mechanics has Newton's laws. Quantum mechanics, as we'll see, has Schrödinger's equation as a key law. Was Newton right? Well, quantum mechanics should be a superset of classical mechanics. Anything that can be explained using classical should be explainable using quantum. But you'd be nuts to try and do billiards with Schrödinger equation, but you could. And you might ask the question, how does the Schrödinger equation reduce to Newton's equation when you see the Schrödinger equation with its language of wave functions, partial differential equations, probability densities and so on? That's language utterly different to Newtonian mechanics, F equals ma. But when I write down a key equation of quantum mechanics, I should be able to derive Newtonian mechanics as a limit case. And that process, and you may be shocked to hear this, is still incompletely understood. That's a shocking thing, right? The third year quantum mechanics you learn, as encapsulated by Schrödinger's equation, will learn how to turn the quantum mechanics off and get Newton's equation. But the full understanding of the passage from Schrödinger theory to Newtonian mechanics is still not properly understood either by the physicists or by the mathematicians. And that's a slightly shocking thing and a humbling thing, and also one of the reasons why there's so much open work left to do in science, in physics. I think I'm going to finish early today. That's the only time I'll do it, but I'll finish early. Please pick up the lecture notes from the front if you haven't already, and I'll see you all later. Please note, by the way, that there'll be no tutorial on this Wednesday. The full lecture schedule is online. Thank you. Also, always happy to answer questions outside after class.